Okay, so we have two states. So we pick two states in the system. We're going to call these just state one and state two. So state one over here when we start, and then state two at the end. So state one, we're going to call that when this block is squished up against the wall, the spring is compressed, and it's not moving. And then state two is when the block is fully at rest. So the way that we use our conservation of energy equation is we say the initial potential and initial kinetic energy at the state that we picked, plus some non-conservative work term, and this is what happens in between state one and state two, is equal to the final potential energy and the final kinetic energy. Okay, so this in-between state, what is non-conservative work? So non-conservative work, you'll often see it represented as some force times the distance times cosine of the angle between them. And it's if there's an external force that's acting and adding energy to the system or taking it away. So in this case, friction is going to be this non-conservative force that's acting in the middle, and it's going to be taking things away. So think about, do I have an extra force on the outside that's adding or taking away energy? Okay, so let's talk about this section. Okay, so for state one, we have a compressed spring against the wall. Okay, so we need to look at the potential energy and the kinetic energy. Okay, so for potential energy, we have actually potential energy due to this compressed spring. We're not any height off the ground, so we don't have any gravitational potential energy. It's not going to fall. We're treating this as our zero height. And then for kinetic energy, we have zero, right? Because it's not moving in the beginning. Okay, so the equation for spring potential energy is 1/2 k delta x squared. This delta x is just how much the spring is compressed or stretched away from this equilibrium line. So equilibrium is like when the spring doesn't have any potential energy, it's happy where it is, it doesn't have any force stored in there. If it's away from the equilibrium point, there's actually this spring force that's trying to push the spring back to equilibrium if it's compressed this way, but if it was stretched this way, it would be kind of pulling that spring back, right, to rest. So hopefully that part makes sense. Okay, so this general expression for the potential energy for the spring, this delta x is just the compressed or stretched distance away from an equilibrium line. Okay. Okay, so cool. So we have potential energy there. For our non-conservative work, we have the friction times the distance, because remember, this is what happens in between. So in between, we have this friction force that's acting against, and it's going to be taking work away. So the reason why this expression is this negative frictional force times the distance is our work expression is the dot product between a force and a distance. And a distance vector. So we have the force, so it turns into the solution to the dot product is the magnitude of the force times magnitude of the distance times the cosine of the angle between them. For friction, because these two, the frictional force, right, is on the same line. Well, in this case, the frictional force, right, is acting along the same line as our here we have our distance vector, right? So there isn't, the angle between them is 180 degrees. So we have this negative value. So actually we're taking work out of the system. So you don't really have to worry too much about the angle. I actually would just kind of think about it as like, okay, well, we know that they're parallel to each other. So we're going to have this F times D, and we're going to make it negative because it's taking work out of the system. It's acting, it's taking energy out. Okay. Then at the end, we have zero potential. The spring is not touching the block anymore, so this mass is not experiencing any potential energy from the spring. And we don't have any kinetic energy because it comes to a stop, okay? So all we do with the information that we have here is we just plug everything into this general expression for conservation of energy, and then we can just solve for this distance term right here, okay? To recap, so for problems like this, we can just use conservation of energy. If we're not asked to find the changing kinetic energy for like one specific object or anything like that, we should by default try to use conservation of energy for these problems. Okay, so by default we should try to look at the initial potential and kinetic. So we just like choose a state, we ask ourselves what energy exists there. We might have to ask ourselves what happens in between if there's some friction or some outside pushing force. And then we look at the end and say, okay, well, now at this end state, what potential and kinetic do we have left? Okay. So we just set up the equation, we look at the states, try to figure out the terms, and then we just plug them in. Okay. So just kind of be careful about whether the work is going into or out of the system, okay, for this term, because this will make it positive or negative there. Yeah, let me know if you have any questions. I know this is kind of a lot there, maybe more than you were looking for, but I hope that this helps clear it up.